Okay, this is a video to fill in some gaps from section 5.1, just some things that we had to gloss over to get to the main points. The first one is we already talked about if you wanted to see if a function is one-to-one from a graph, you do the horizontal line test and the vertical line test. It has to pass the vertical line test first to be able to even be considered a function. And then if it passes the horizontal line test as well, it is a one-to-one function. So how do you tell that if your graph is not there and you just have an equation? The way we prove it is that we set two y values from the same function equal to each other, which we're just calling them f of a and f of b. We plug that in, essentially just substituting x for the variable, and we try to prove that this actually does equal a equal b. If we do that, then that means that the x and the y were both unique. So when we do b minus 2 times 1, a minus 2 times 1, you add 2 to both sides and you have proved that b and a are identical. They are the same x and the same y goes to each of those. Here's a case where it would fail. If you do f of a equals f of b, here you get a squared plus 4 and b squared plus 4. You subtract the 4's, and the problem is we don't know if a and b were exactly the same. The reason is you could have had negative 3 squared equals positive 3 squared. Yes, they both equal 9, but the numbers originally were not the same. So that's why we would say in this case, not one-to-one. Now, for things and parabolas, the reason they don't pass the horizontal line test, so that makes sense. But if you wanted to use a parabola, you'll see in one of my examples in a minute, we restrict the domain, and then we can say, okay, on this piece of the parabola, it could be one-to-one. All right, let's look at the next example. This is one we skipped in class because it was just trying to prove that using the theorem on inverse functions, we want to prove that they're inverses, and then we want to plot them together. The inverse test says that if you want to prove by theory that two things are inverses, you do composition one way and show that it equals x, and you do composition the other way and show that it equals x. That proves that they reflect over that line y equals x. So if we do f of g of x, remember you write the f function with a blank for the x, you plug the g function in, we square that, that would be just x minus 5 because negative 1 squared is 1 and you square the square root. And notice that that does equal x. G of f of x, we take the g function, which is negative, parentheses, or excuse me, square root, and then instead of x, we're going to write a blank. Sorry. So that would be blank minus 5. We plug in the f function, which is x squared plus 5. We get that this is negative square root of x squared, which makes you think that is negative x, and it is, except remember in our domain of this guy right here, all x's, because that's the one we plugged in, side, which is the interior, all x's are less than or equal to 0. That means that this is a negative negative. So that actually means it's positive x. So by the theorem, these two actually are inverse functions. So if we plot them, you can just do a table of value for each. So this says our x's need to be less than or equal to 0, so 0, negative 1, negative 2. If we plug in 0, that would be positive 5. Negative 1 squared is 1, plus 5 would be 6. Negative 2 squared is 4, plus 5 would be 9. And that's all I have to do, really, because if I plot one, I know that they're already inverses. The other one's just the ordered pairs flipped. So negative 1, 6, and negative 2, 9. So notice it's half of a parabola this way. And this guy should just be the reverse of those. And you can check the points individually if you want, but it should be 5, 0, 6, negative 1, and 9, negative 2. So we get 5, 0, 6, negative 1, and 9, negative 2. So notice those are reflecting across that y equals x line. Okay? We did a couple of these finding the inverse problems in class. I'm going to finish off with the ones we had to skip. So to find the inverse, remember you have to do a couple things. First of all, we have to know it's a one-to-one function. Everything we're going to give you is, but that's something you would have to check. So then we write this as y equals 1 over x plus 3. We physically swap the domain and range, so we swap our x and y's. And we try to resolve for y. So this would be, think about cross multiplying, that would be x times y plus 3 equals 1. Distribute, that would be 3x. I would subtract the 3x over to the other side and then divide everything by x. So my inverse would be 1 minus 3x over x. We said we would talk about the domain and range of each, so f and f inverse with their domains and range. In the original, x could not be negative 3. In the ending inverse, x could not be 0. So x cannot be negative 3. X cannot be 0. When you do the inverse and the original, remember their domain and ranges flip. So this is y can't be 0 and y can't be negative 3. Okay, let's look at another one. This one is a parabola that has been defined as x's are greater than or equal to 0. That way we know we have only half of the parabola. And we would swap our, well, first of all, we have to write it as y equals 5x squared plus 2. We swap our x's and our y's. We try to resolve. Divide by 5. Now, when you go to take y squared, remember you're going to be taking a square root to get rid of that. Normally we would write plus or minus all of this, except we knew that our x's were greater than or equal to 0 in our original, which means our y's are greater than or equal to 0 in the inverse. So we're only going to go with the plus case. And then this would be f inverse of x equals the square root of x minus 2 over 5. If you needed to rationalize, which we normally do, we would multiply top and bottom by square root of 5s. So that actually makes that f inverse of x equals the square root of 5 times x minus 2. You can distribute that if you want or not over just 5. Okay, so to figure out our domain and range, for this original one they already told us, which means this y is greater than or equal to 0. This one you have to be careful, this is underneath a square root. So if you had 5x minus 10, if you distributed that, remember a square root has to be greater than or equal to 0. So this is for our domain, and that would mean x is greater than or equal to 2, which means y is greater than or equal to 2 in the original function. Okay, looking at the next one, we have a cubed function. So y equals negative x cubed plus 2. We would swap the x's and the y's. Try to resolve for y. Divide that negative out, so negative x plus 2. Take the cubed root. And remember, the nice thing about the cubed root is you don't have to worry about signs, because whatever this sign is, you're going to get the same sign over here. So we don't need to write a plus or minus. So my inverse would be cubed root of 2 minus x, if you want to write it with the negative not being up front. And domain and range of the original versus the inverse. This is a polynomial, so that's all real numbers, which means this is also all real numbers. And this is a cubed root, which is also all real numbers, which means the range of the first one was also all real numbers. So nothing interesting really for the domain and range there. Okay, let's look at this last guy. It is f of x equals negative x. So if we do, that would be y equals negative x, swap, resolve for y, or just dividing that over. Its inverse is its actual same function. That's rare, but sometimes it happens. And then for domain and range, it's again not that interesting. because they're both polynomials. So it's all real numbers for both domains, which means both ranges are also all real numbers. And that catches us up to the end of the 5.1 video.